little bit like a step backwards in terms of complexity. Um, but it's really the reason for that is that it's a segue into something different. So, plain simple wave equation with this number c squared equals 1, all right? And Dirichlet boundary conditions, homogeneous Dirichlet boundary conditions. The only thing that's a little bit strange is I'm going to stretch out the boundary a little bit. And this is really just more for convenience. Um, I could have rescaled the whole problem to fit within 0 to 1, but whatever. 0 to 6 is the domain. Dirichlet boundary conditions. The only thing that's going to be a little unusual is our initial condition. And it's actually easier to just graph it than it is to describe it. But I'll go ahead and do that. 0 if x is from 0 to 2. And then we're going to do x minus 2 if x is between 2 and 3. And then if x is between 3 and 4, we're going to let this be 4 minus x. And then 0 again if x is between 4 and 6. All right. And what is that? It's just a bump with 0 on both sides. All right. So the whole idea here is that we have an initial condition that only exists in the middle, and then there's nothing on either side. Okay. And this is going to help us understand a little bit more what was going on at the end of class on Friday. We saw at the end of class on Friday, I was standing at the left-hand side of the domain. I was shaking a rope up and down. That rope was attached to a frictionless hoop over here on the right side. And it looked like for a while, information like waves were traveling out from myself to the right. And then they appeared to be hitting the wall, and then all kinds of crazy stuff happened. And then after a while, it looked like waves were coming back at me, even though I was the one shaking them. It was weird. It was very strange. And so this example turns out is going to help us understand what was going on there. And finally, the second initial condition ut of x and 0, also 0. Okay, so this is structurally very simple problem. No forcing function over here, no time dependent boundary conditions, and just a simple initial condition here with no initial velocity. All right. So in terms of the overall structure of the problem, it's pretty straightforward. All right, so there are no non-homogeneous boundary conditions. I do not need to split the problem. All right, I can go directly to looking for a transform. And in order to find the transform, I need to find the eigenfunctions. All right, so that's my next step. Eigenfunctions. And I need to identify the spatial operator. Here it is. Nothing complicated here, but it's worth explicitly taking the time to do that. And so my spatial operator is going to be L phi equals phi xx equals minus lambda phi. And so my ODE is going to be phi xx plus lambda phi equals 0. And the only thing that's a little unusual, again, is this domain. I've got phi of 0 is 0, and phi of 6 equals 0. All right. So other than that 6, oops, this is a problem that we have done many times before. I am only going to consider the case lambda positive. r squared plus lambda is positive, so r is plus or minus the square root of negative lambda. The dividing case is 0 in that case, and so I'm going to consider the numbers of the values of lambda above that dividing case. I'm going to get phi of x is c1 cosine root lambda x plus c2 sine root lambda x. Phi of 0 is c1 is 0, and then phi of 6 is going to be c2 sine of 6 root lambda. Also has to be 0. So in order to make this true without realizing the trivial solution, I need to have 6 square roots of lambda equal n pi. Lambda n equals n pi over 6 quantity squared, and phi sub n of x equals sine n pi x over 6. All right, so just the 6 in the denominator here inside the eigenfunctions. Everything else is the same. Then I'm going to have a transform. All right, and as usual, my transform is defined in the standard way. This operator, I should note, we saw this operator many times back in chapters 2 and 3, and we know that this operator is already in Sturm-Liouville form, and so the weight function is just 1. Because it's already in Sturm-Liouville form, it's already self-adjoint. We don't need a weight function to make it self-adjoint. So all the nice things that are true of self-adjoint operators will be true here. So the transform of any function will be the integral from 0 to 6 of that function times sine n pi x over 6 divided by the integral from 0 to 6 of sine squared n pi x over 6 dx. And that denominator is going to be 3. It will be 1/2 of the quantity 1 minus cosine n pi x over 3. And then when we integrate that, we'll get x minus the sine of n pi x over 3 divided by n pi over 3. And we'll evaluate that sine term from 0 to 6. It'll vanish, and we'll just be left with the x term from 0 to 6, the 1/2 x, which will give us 3. Okay, and so we can write this in a little bit more compact form. 3 times the integral from 0 to 6 of the function times sine n pi x over 6 dx. Boy, I'm having a hard time writing 6s today. There we go. And the inverse transform is the standard sum over the eigenfunctions. Now, this is going to be a little bit anticlimactic. I'm actually not going to do the messy calculation that's about to be demanded of me. But I will keep going, just spend a couple more minutes finishing out the mechanics of this problem, just to reinforce the procedures that we've been learning so far. Having identified the eigenfunctions and identifying the transform, I now apply the transform to my original problem up here. All right, and so I take the transform of UTT equal the transform of UXX, and then I have my UX of 0 equals, and I'm just going to call that function I naught of x. And then I've got I take the transform of both sides of that equation. And then I have my time derivative initial condition. And that's just 0. All right, so I have to take the transform of all 6 of these things. Hopefully we're getting comfortable these days with what we do. With all the different things, I have here the transform of the second time derivative. That is, first take the time derivative, then take an integral in x. Since x and time are independent variables, I can change the order of operations. I can first take the transform and then take the second time derivative. Here I have the transform of L acting on U, and that is always minus lambda sub n U sub n.
Professor?
Yes?
Was the boundary condition u of t x0, was that given?
It was 0, yeah.
Alright.
Up here at the
Must
top.
have not wrote it down. Thank you.
All right, and then here I have a very similar thing. I'm first setting t equal to 0, then integrating an x. Well, there's no reason I can't do those in the opposite order. So first I can take the transform and then set t equals 0. This is some function, and I take the integral transform and I get some number. I'll call that number I0n. Here, first take the time derivative, then set t equal to 0, then integrate in x. There's no reason I cannot first take the transform, then take the time derivative, then set t equals 0. And the transform of 0 is 0. All right, so we end up with a very simple ODE. Second order ODE, no forcing function, one non-zero initial condition. This is pretty straightforward. I can solve this since I've already found the values of lambda n. They're positive. I know that this is going to be sines and cosines in time. And I will get un of t equals c1 cosine root lambda n t this time, plus c2 sine root lambda n t. It's kind of a coincidental feature of the wave equation that you get the same type of solutions in time as you did when you were solving for the eigenfunctions in space. Because you've got this two time derivatives on the left, two spatial derivatives on the right, you get this same structure, but that's really more of a coincidence. And it's only true of the wave equation. Now I satisfy my initial conditions, un of 0. That is going to be down here, sine of 0 is 0. So I'm going to get just c1, cosine of 0 is 1. And that equals I0n, whatever those are. And then un prime of 0, the time derivative, is going to give me c2 root lambda n cosine of 0, which is 1. And that's going to be 0. So c2 equals 0. And my final solution is un of t I0n cosine root lambda n t. And then my final solution to the whole problem, u of x and t, is the sum, n from 1 to infinity, of cosine. Let's go back and remember, what is root lambda n? Root lambda n is n pi over 6t times sine of n pi over 6x times I0n. And I0n remains to be calculated, right? I0n is going to be 3 times the integral from 0 to 6 of I0 of x times sine n pi x over 6. But remember, the way I0 of x is defined, it's actually 0 between 0 and 2. So you're not going to get any contribution from x 0 to 2. So I'll write like 0 here. And then I have another piece of integral from 2 to 3 of x minus 2 sine n pi x over 6 dx. And then I have another piece of integral from 3 to 4 4 minus x times sine n pi x over 6 dx. And finally, I have another piece of integral from 4 to 6, which is 0. Okay? And that 3 is the 1/3 denominator that we pulled out front. And so this is going to be our I0 of n. And I'm actually not going to do this, right? You go and you calculate and you get numbers. And I could spend the rest of the class time just doing this exercise in calculus. Instead, what I want to do is just show you the video. Okay, so it's all done here except the calculus. Let's pull up the solution video. All right, here I have it. All right. Let me see how to share it. All right, can you see it? Yes, no,
Yes,
I can't.
sir.
Good, okay, good. So here's our initial condition. I actually was not able to pause it right away at the beginning. So this is actually 1/10 of a time unit into the solution, but pretend it's not. And we have, 0 to 6. Our little triangle goes from 2 to 3 and then 3 to 4. And that's our initial condition. And now we're going to play it and we're going to see what it does.
Professor,
Yes.
what would be like a real life example of something like this?
Well, it's a little bit of a contrived initial condition. Because in order to realize an initial condition like this, you would have to sort of pull up on the middle of the string, but simultaneously push down at x equals 2 and x equals 4 in order to keep the regions from 0 to 2 and 4 to 6 flat. So this is not the most physically relevant example, but it does show us some behavior of the wave equation in, I would say, a little bit more detail. So it's contrived for a purpose to show us how the wave equation behaves, right? And what you see here is that we have very well defined what we would call traveling waves, right? Moving to the left and to the right, all right? And then they begin interacting. So what first appears to happen is we have a tall triangle, okay, that's of height 1. Let me see, and I really apologize because I'm not able to go frame by frame somehow over okay, time t equals 0, perfect triangle, height 1. Width 2. It's 2 wide and 1 tall. All right. Now I'm going to try and stop it at time t equals 1. Let's see if I can. Okay, not quite, but close enough. By time t equals 1, the triangles have moved. Okay, it appears that the big tall triangle that goes from 2 to 4 has split into 2 triangles, each one half the height of the original. Right, so we have one triangle moving to the left, one triangle moving to the right, and they're each now half as tall as the original triangle. Note that in one time unit, the triangle moving to the left has moved one space unit, right? And the triangle on the right has moved one space unit to the right. All right. So this is actually where the interpretation of the number c comes from in the wave equation. That's c squared, right? Where c squared equals tau over rho. And I said we'll find this interpretation of the value, the meaning of the number c later on. Well, c is the speed with which these waves move to the left and right. All right. So we call c the wave speed. And we have here a triangle moving to the left with speed 1, a triangle moving to the right with speed 1. I'll try and top the timer at time t equals 2. Now the triangles have hit the Dirichlet boundary conditions, and something sort of strange ends up happening. It's not really clear what's happening yet, but by this point, what seems to have happened is that those triangles have bounced off the boundary conditions. They've bounced off the Dirichlet boundary conditions, and they've been reflected back into the interior, but upside down. All right, just visually looking at what's happening, I now see upside down triangles. The one that was moving to the left is now moving to the right. The one that was moving to the right is now moving to the left, and they're both upside down. Other than that, they're the same shape. They're just upside down. All right, and then now at time 6, they appear to have like remerged into a single triangle upside down with height 1. But one time unit later, they're now no longer merged. They're moving back and forth to the left and right. What's actually happened here is that those two triangles have passed through one another. And as they were passing through one another, their values added. All right. So for a moment, they were tall. And then they passed through one another, and now they're half height again. Again, they reached the Dirichlet boundary conditions. What we saw last time traveling waves hit the boundary conditions is that they did something sort of complicated looking, and then they bounced off and came back towards the interior upside down. Well, if these waves bounce off and come back upside down, we should expect then right side up triangles to come back towards the middle. And something weird is happening. And now we have those triangles coming back towards the middle. And finally, they pass through each other one more time and they merge. And then we could loop this. We could loop this as many times as we want. Okay. It's interesting that here with this domain that is 6 units wide, we see these triangles behaving as distinct left and right moving waves. But in a previous example that we looked at, and let me see if I can find that. Let's see, was it 1? Was it 2? It wasn't 1. Yeah, it was. It was this one. Can you guys still see my screen?
Yes, sir.
Yeah, we can see the
weird
graph.
bouncing up and down.
No, the movie's paused, but
Okay, so I need to share.
That's moving for me.
Oh wait,
Yeah,
that's
mine
weird.
was moving.
oh,
You know what? Let me
maybe
just,
mine's just the internet. I don't know.
Let me just kill it. Let me. Yep. Screen sharing has stopped. I get it. Open up a new one. There we go. So now hopefully you can see this example that we looked at a couple classes ago. This is the same equation. All right. It's the same equation. In fact, it's the same, very nearly the same. It's in fact exactly the same initial condition, right? It's a triangle that is 2 units wide and 1 unit tall. It's just that in this problem, the domain only goes from 0 to 2. And so in effect, there's nowhere for the triangle to go left and right, like it's sort of trapped. It's interesting that the same equation produces these 2 different kinds of behavior. This video that we're looking at right now very much seems to be what you might call like a standing wave or some sort of modified standing wave. Like the shape isn't changing. It's not moving to the left or right. It doesn't look like it's moving to the left or right. It's just kind of moving up and down in this kind of weird way that the tip of the triangle disappears and becomes flat and then reappears at the bottom upside down. So this is quite different seeming behavior from what we just witnessed on the domain 0 to 6. But in fact, it's the same equation. Nothing really changed except the size of the domain. And in the wider domain, we can clearly see these left and right traveling waves. We can now very much interpret the value of the constant c, the left and right traveling wave speed, and we're now that actually is going to inspire another way of looking at this equation and its solutions. Does anyone have any questions over the videos that we've watched? The differences between these two videos and the equations that generated them? All right. So we didn't calculate these, we watched a movie. So what I basically want to do then is say, on the one hand, I want to say what is going on. It seems very remarkably easy to describe what is happening visually, and that might be a little bit surprising given how much time we've spent trying to understand partial differential equations, how much time we've spent on on transforms and eigenfunction expansions. All of that sort of feels complicated, and at least when we looked at the diffusion equation, it was not easy to describe concisely everything that was going on. But here with this wave equation, it seems like we really can. The initial shape that you start with kind of splits in half. Half of it moves to the left, half of it moves to the right, and then they bounce off the boundaries, possibly upside down. Right? You can describe that in like one sentence. So I want to take a little bit of time to analyze why mathematically we're seeing what we're seeing. Okay, so let's look once again at our eigenfunction solution. All right. Oh, shoot. Can I get it to paste right here? I cannot. Only seems to want to paste right on top of itself. All right, I give up. Just rewrite it. It turns out we're going to once again appeal to a trigonometric identity. All right, and it turns out that cosine A sine B can be written. Just look up in my notes because I do not remember these things either. Here we go. That can be written one half times sine A plus B minus sine a minus b. All right, that's an angle addition result of two angle addition formulas. And so we can write this accordingly. We can say that that is I0n over 2 times sine, what would be a plus b? A plus b would be n pi over 6 t minus x minus sine n pi over 6 t plus x. All right, which is actually quite interesting. We could go further. We could say 1/2 times a sum from 1 to infinity of I0n sine n pi over 6 t minus x plus another sum I0n sine n pi over 6 t plus x. And we see, oh, there it is. This whole thing right here is a function of, we might write it in the form x minus t, is the more conventional form. It's just negative t minus x. Whereas this thing here is a function of x plus t. So it's no longer a function of x and t separately. It's a function of nothing more than the difference of x and t, whereas this one is a function of nothing more than the sum of x and t. And this is very interesting. So it's worth exploring what happens to a function like this. All right, and a function like this. What does it mean to be a function of x minus t? Well, it means that suppose t increases by 1, but suppose x increases by 1 as well. Then you have exactly the same value you started with, right? Whatever the function f is at the point xt where you start, if x and t both increase by 1, then you have the same value of f. All right, and so what that means is that whatever value I start with at some point x, here's that spatiotemporal diagram again, it just translates to the right with slope 1 in the spatiotemporal diagram, or with speed 1, how we would call it. Right? So if I have a triangle, that triangle is just going to move to the right with speed 1. Whatever f is, whatever shape this is, that shape is just going to move to the right with speed 1. Conversely, what does it mean to be a function of just the quantity x plus t? Well, if x decreases by 1 and t increases by 1, then I'm back where I started. So whatever value I start with here is going to translate to the left as time increases. And so if I have a little triangle, it is going to move to the left. So this is some function, some shape traveling to the right with speed 1. This is some shape traveling to the left with speed 1. And look, they're each half as tall as the original. All right, so this use of a trigonometric identity really helps us understand what we're seeing. When we apply that identity, we regroup the terms according to the ones that are only functions of x minus t, the ones that are only functions of x plus t, and all of a sudden, what we observe makes sense. It comes right out of the math if I'm willing to play with the equations a little bit. This observation ultimately is not specific to this particular problem. All right. There you can show that any solution of the unforced wave equation UTT equals UXX has this property. Can be written U of X and T equals F of X minus T plus G of X plus T. All right. And it's a property of this structure of this governing equation. All solutions, no matter what the boundary conditions are, can be written in this form. And that is a very general result for this unforced wave equation. It's also potentially useful from a solution standpoint for this unforced wave equation because the nature of the solutions to the wave equation tend to be such that there's no smoothing that ever gets applied. All right. You know how when we looked at the solutions to the diffusion equation, that first example, there was started out being a little bit of Gibbs phenomenon at the very beginning, but it was quickly smoothed away by the properties of the diffusion equation itself. The diffusion equation exhibits the decay of its modes at a rate proportional to their wave number. So the more quickly oscillating a mode is, the faster it decays. And so, Gibbs phenomenon is the prevalence of these high frequency modes, and the nature of the diffusion equation is to very quickly suppress them, which is great, right? So if you're trying to solve a problem using this method and you're like, oh man, my initial solution has Gibbs phenomenon, it's no big deal because the diffusion equation is going to very quickly get rid of it. The wave equation, on the other hand, has no decay terms. There's no e to the minus anything, no e to the minus k, e to the minus lambda n t. The whatever you start with is sort of what you keep forever. And so if you have corners or jumps to begin with, those corners or jumps are going to persist forever in your solution. And eigenfunction methods are going to be a little bit difficult to apply. You're going to need lots and lots and lots of terms, especially if you have jump discontinuities. And even if you keep those lots and lots of terms, you're still going to have some Gibbs phenomenon hanging around. So it's interesting that at least without forcing, if there's no forcing, your solutions have such a simple form. And it suggests that for this specific situation, we might explore the consequences of this form a little bit more, really try and understand how these left and right moving waves behave, what happens when they hit a boundary, and so on. All right. And this leads to a method of thinking about this unforced wave equation called the method of characteristics, which is the study, the topic of Unit 6. Right. So I'm not going to say anything more about that, but to sort of pose this possibility that this unforced wave equation has, in the end, this very simple structure that we can exploit in Unit 6. What I do want to say, though, you might be thinking at this point, like, well, if I can solve the wave equation this way, like, why did we do all that other stuff? And what I'll say is that this form only works for the unforced wave equation. So the minute you throw a forcing function on there, it breaks down. The minute you have, time-dependent boundary conditions that introduce forcing functions in your interior problem after you split the boundary problem and the interior problem apart, this approach can break down. If, as we do in your homework assignment, we throw a damping term in there, plus delta ut, which you might remember from ODEs, this approach breaks down. All right, so what we're going to do in Unit 6 is kind of a highly specialized approach for a very narrow subset of all possible PDEs. But the wave equation is so important that this approach has been fleshed out by people, because this vanilla wave equation is common enough that it's worth having this extra tool at our disposal. So this kind of concludes our study of the solution of one-dimensional PDEs using eigenfunction expansions. You have all the tools that you need: boundary separation, finding eigenfunctions, finding transforms, taking transforms, solving ODEs, inverting. And we can do that for boundary value problems with no time derivatives. We can do that for, let me just actually take a moment to review that. If we have a boundary value problem, right, that is something like LU plus F equals 0. Or if we have a diffusion equation that says LU plus F equals the time derivative, or if we have a wave equation that says LU plus F equals the second time derivative, all these problems can be solved the same way. And when you take the transform, you get UN minus lambda sub n u sub n plus f sub n equals 0, minus lambda sub n u sub n plus f sub n equals un prime, or minus lambda sub n u sub n plus f sub n equals un prime prime. Or if in the homework, you could even say damped wave equation UTT plus delta UT equals LU plus F. You get UN prime prime plus delta UN prime equals minus lambda sub n U sub n plus F sub n. Right? So all of these problems have this spatial operator that gets transformed into multiplication by a constant. And that's why we do this approach. We will spend, like I said, Unit 6 on a more highly specialized approach for a specialized subset of these equations. But this set of tools right here, we're basically done with at this point. Anybody have any questions?
Can you upload the movie with this homework in the, I mean, with these notes?
Yep, I'd be happy to.
Thank you.
I'll just put it in with the lecture notes, the video notes.
Awesome.
Yep. I'll put both movies in there. Any other questions? Otherwise, you're free to go. A couple minutes early today.
Have a nice day.
Yep, you too.